Hello and welcome. In today's lesson, we'll talk about the limits of polynomial, rational, and square root functions. This lesson has been prepared for students who are taking the Calculus and Vectors course, and we are on the unit of limits, lesson 1. So let's get started. Very often in everyday life, we encounter problems that can be modeled by equations of various functions. And the solving process, naturally, entails the need of using or evaluating a function at specific point. As an example here, I brought in the equation of the function f of x equals 2x minus 3, and we are about to evaluate this function at x equals 4. So to evaluate the function at x equals 4, let's say we have to find f of 4. So wherever you see x, you replace it by 4. 2 times 4 minus 3. So we're going to say that f of 4 equals 8 minus 3, or 5. So the value of the function at 4 equals 5. Now this evaluation process is also described as evaluating the limit of the function at a point. So I'll write it down here. And the way we write it is this: the limit as x approaches 4 of f of x equals the limit as x approaches 4 of 2x minus 3. And now it's time to evaluate it. 2 times 4, we let x equal 4, minus 3 equals 5. So we're going to say that the limit as x approaches 4 of function f of x equals 5. So as you can see in this example, the value of the function at 4 equaled the value of the limit at 4. And we say that this function is continuous at x equals 4. Now you're probably wondering, why do we have to take the limit? Because the process, as you can see, is pretty much the same. Or is there anything else that we don't know about limits and we need to? So there is a lot more to a limit than just a simple function evaluation. And to illustrate this, I brought in the example of function g of x equals x squared plus 4x minus 12 over x squared minus 2x, and we'll evaluate it at x equals 2. So I'm going to start by substituting x by 2, and then this will turn into 2 squared plus 4 times 2 minus 12. Denominator 2 squared minus 2 times 2. So that would equal 4 plus 8 minus 12, 0. 4 minus 4, 0. If you ask the calculator will give you an error, and that is because the function is undefined at this point. So we just found out that the function is undefined at x equals 2, which means that the function has no estimatable value at x equals 2. So very often when we are solving these problems, even though we are unable to find the value of a function at a specific point, we need to know what happens to the function around that point. Or in other words, we need an estimation of the y values around x equals 2. And that's what the limit of a function does. So the limit of a function, remember this, can give us an estimation of the value of a function at a point, even when a function is not defined at that point. If this sounds a bit confusing to you, I'm pretty sure it will become a little bit more clear as we move on to an example. So this is how we will find the limit in this particular function. So g of x is given. We don't know what the value of a function at 2 is, but we want to estimate what happens around 2. So what we are going to do is we're going to approach the number 2 from the right and from the left side of it. To those of you who are not familiar with the terms 2 minus and 2 plus, here I'm going to go over and explain it to you very briefly. So pretend this is a number line, and this is where number 2 is sitting somewhere on the number line. So To approach number 2 from the right hand side of it, okay, we mean that the values of 2 are getting closer to exact value of 2. Numbers like this look like 2.01, 2.001, 2.0001, and so on. Okay, and 2 minus would be all the numbers to the left of 2, and numbers such as 2 minus would be numbers like 1.9, 1.999, and so on and so forth. So for the values of 2 plus, I took 2.5, 2.1, 2.01. So as you can see here, the values of x got closer and closer to x equals 2. And in return, I got the values of y getting closer and closer to the value of 4. As you can see here, the difference or the gap in the values is pretty large, and it becomes almost insignificant in the last 2 values of x. So we got 3.99985. So in this case, we're going to say that the limit of g of x as x approaches to from the right hand side of it would equal almost 4, not exactly 4, but a little less than 4. So we say 4 minus. On the other hand, in the same way, we evaluate the function as x approaches to from the left-hand side of it, and we find out that the values of y get closer and closer to 4. So as you can see here, the gap between the y values is larger, and it narrows down and becomes insignificant for the last 2 values of x. So in other words, here we're going to say that the limit of the function as x approaches number 2 from the left-hand side of it would equal, would equal 4, but not exactly 4, a little bit more or slightly more than 4. Now, to illustrate this a little bit more, I brought in the graph of the function around x equals 2. So this is the function gx, and at x equals 2, the function gx has a hole. That's because the function is undefined at x equals 2. You probably remember from the functions course that it seems that we had a removable asymptote in here, okay? So removable discontinuity. Now let's take a look at what happens as x approaches number 2 from the left. As x approaches number 2 from the left, right, all the values of y are higher than 4. And that's what the limit gave us. And then as x approaches 2 from the right, all the values of y are below 4. Okay, so 3.999. So in this case, we are going to say that the limit as x approaches number 2 from the left for function g of x equals the limit as x approaches 2 from the right. Okay, and it equals 4. Okay, again, this is an estimation. So in this case, we're going to say that the limit of a function exists, and if we were asked to find the limit at x equals 2, not 2 minus or 2 plus, but exactly out at 2, we're going to say that the limit equals 4. So in here, we just discovered one very important rule about limits that explains the continuity of a function. So if both left and right hand side limits are equal to each other, then the limit at that point exists. Notice again that A function doesn't have to be defined at a point in order for its limit to exist at that specific point. So, and that is the power of the limit, or the advantage of the limit. So in general, the limit of a function is written in this format. So L represents the value of the limit, and that's the way we read it. The limit of f of x as x approaches a, and we say approaches a because most of the time evaluating the limit of a function is an estimation process. Okay, it's not an evaluation, a pure evaluation process. And it means that the values of f of x will approach L more and more closely. They don't have to necessarily be equal to L as x approaches more and more closely from both sides of A, where x is different than A. Now, bringing back the example, the first example we looked at, the limit of the function at 4 here was the same as the value of the function, so we say the function is continuous. And sometimes the limit of a function at a point doesn't equal the value of a function at a point, or in our case, the value doesn't even exist, okay? So in this case, a function is discontinuous, all right? Now we're going to learn how to find the limit of a function algebraically. So let's get started with this very simple example. Limit as x approaches to x squared plus 4x minus 12 over x squared minus 12 and minus 2x. You probably recognize in here that this is the equation of the function that we were just analyzing. So we're going to say that first thing I want to do is substitute x, but I already tried this, and it seemed that direct substitution of x wouldn't work in this case because the value of the limit or the function at this point is not definable, okay? It doesn't exist. So now we're going to have to try to find the limit differently. Step 1, factor both numerator and denominator. So in this case, we have x plus 6 times x minus 2, the factors of the numerator, and denominator is x minus 2. As you can see in here, x minus 2 and x minus 2 simplifies. That's a removable asymptote we were talking about. So the function was supposed to have an asymptote at 2 and at 0, but these two factors simplified. So now the limit has changed to become the limit as x approaches to of x plus 6 over x. Now we're going to try to substitute x by 2 and see if we can evaluate this expression. So 2 plus 6 over 2 would equal 8 over 2 or 4. So therefore, we're going to say that the limit as x approaches 2 of x squared plus 4x minus 12 over x squared minus 2x equals 4. Now, in today's lesson, we are going to learn how to determine the limit of various functions, and we are going to start with polynomial functions. Now, there are various types of limits, and we're going to break them down into groups so we better understand the strategy to evaluating each and every one of them. I'm going to stop the video at this point. So this will be the first part of lesson 1, and I will continue the lesson with the simple limits. See you in a bit. Thanks for watching.